Okay, ladies and gentlemen, hello and welcome. I hope that you can hear me and see the slides as shared by César and Team Up. I do welcome you now today on our second session on Space, which is on safety and performance. And I still see that people are joining, so I would probably stick to the unwritten rule of online meetings where usually the first 4 minutes are allocated to letting everyone into the session. So I will just chit chat away for a couple of seconds more because I see that still names are popping up. So let me welcome you. This is actually the last session for the day and for SIDS. It is such a close session, and we will see some interesting parts coming at the end of today as well with the Young Scientist Award, the winners of whom are going to be announced in the afternoon meeting. It's very nice to see a lot of names, and some of them are familiar, so welcome to all of you. And now it's my turn to introduce myself. My name is Dr. Rita Shamoni. I'm from Hungaro Control, head of strategy and project management department. And I have the honor to have been involved into the SESAR Scientific Committee as a member there since 2017 already. And it's always my pleasure to take part in the SESAR Innovation Days, where it's very interesting to see these exploratory research projects that are very promising for the future. And it's always good to see what kind of directions the industry is taking, what kind of new ideas are out there, which are to get evolved in the next coming years, coming decades, and which are then finally integrated into our systems. Let me also introduce the speakers of today's session. You will shortly see a slide with all the 3 speakers of this afternoon. Here you see our 3 speakers. Without taking further time, let me introduce our first speaker, who is a lecturer in ATM and CNS at Cranfield University. Furthermore, he also did this PhD. This he did at the University of Catalonia, and was also a visiting researcher with INAC. Before that, he completed his master's and his bachelor's degree in Nanjing University. And now today he is going to be our first speaker. Welcome, Jan. The floor is yours now. We are really keen on hearing your presentation.
Thank you, Rita. Thank you for the introduction. Please allow me to share my screen. Just a second. It's here. Yes, and now I think it's full screen, right?
Yes.
It's perfect.
Okay, thank you. Good afternoon, everyone. This is Jan speaking from Cranfield University. I'm here today to present to you our recent study in incorporating optimization in strategic conflict resolution service in Space.
And you have 15 minutes to present your research, sorry. Thank you.
Okay. And the presentation contains 6 sections. We will have a quick introduction and walk through some background. After that, we'll introduce how we implement the conventional first come, first served approach, and the proposed optimization approach, as well as how to integrate them under different operational scenarios. Then some results will be given through the illustrative examples. And finally, the conclusions and the future work. Now, according to the Space roadmap, a service named Strategic Conflict Resolution is proposed to realize at U2 stage. And here are some indicative descriptions that we find useful from open literatures. As you can see, we have tried to capture some keywords. And in general, the idea is actually simple. Namely, a flight will be deconflicted given the current situation once its flight plan has been submitted. Of course, before the flight is allowed to take place. Now, having this in mind, let us walk through the background. Now, with a special focus on how we model the flight plans. With regard to the type of operations, generally there are three main types, like remote pilot, automated and information flights. But if we check out their commonality in representing the traffic demand, we may come across these linear and aerial flights types. And specifically, linear flight means that a UAS travels each position for only one time, whereas we consider aerial flight as that certain positions may be revisited by the UAS for multiple times. We have introduced this concept in our previous work, and now we work on the flight plans in a 3D environment in this study. On the airspace side, we consider that it is gridded into a set of identical 3D volumes, and each connected to its adjacent ones in a predefined number of directions. Also, we assume a fixed geographic areas representing the long-term geo zones, like the cylinders shown in the figure, and also time-varying geographic areas for short-term geofences, like these red boxes in the figure. You can see the linear flights trajectories with blue lines and the green volumes occupied by the aerial flights. So when planning those flights, of course, the fixed geo zones and the time-varying geofences will need to be avoided. Next, as stated in chorus, to enable effective operations, the strategic conflict resolution service requires precise operation plans given the 4D trajectory to be flown. Well, obviously, to use the airspace efficiently, it requires the amount of buffer space around flights to be minimized. However, some operations are not very precisely plannable for different reasons. Right? And there are some discussions on how to identify the uncertainty buffers. In this study, we are working on, as we are working on a gridded airspace, it is quite natural to consider the adjacent volumes of the essential point as the buffer volumes. For instance, here, imagine this red volume is the essential volume on the original trajectory. Then we can consider those 6 ones as the buffer volume, or 26, or even more, depending on the precision of the flight plan. This setting actually raises this question. For linear operations, a specific volume can be an essential volume and a buffer volume at the same time. See this figure, example of a linear flight. The left side is the essential volume, the right side is added with the buffers. As you can see, a specific airspace can be an essential volume and a buffer volume at the same time, or it can be a buffer but associated to various essential volumes, as you can see. And this actually changes the way how we define the flight plans for linear flights. And to cope with this, we enforce the time steps of the buffers to remain the same as their corresponding essential volumes. And for aerial operations, it is more straightforward, as the whole period of time will be blocked from takeoff to landing. So the buffer volumes can be considered as a set of extra essential volumes. Now, based on the specific forms of the flight plans we have just discussed, let us first use the Fcfs approach to perform the deconfliction. More precisely, instead of first come, first served, we should probably call it like first submitted or first requested and first served, because the flight plans will be processed according to their submission order rather than the scheduled takeoff or landing time. Thus, an implicit rule would be that the flight plan submitted early will have an absolute higher priority than the later ones, unless there is a very high priority flight that requires a rerun of the process. Here is the pseudo-algorithm for the Fcfs approach. Basically, the fundamental of this algorithm is to have a common airspace representation to indicate the occupancy status of the 3D airspace volumes. Flight plans will be processed one by one. Once a group of volumes have been occupied by some early submitted flights during the specific time periods, they will not be available for the other flight plans submitted subsequently. And those flights will be delayed iteratively until all their concerned airspace volumes have been cleared. And in such a case, the new flight plan will take those time and space and extend the occupancy time with the length of the separation minima. So basically, this algorithm can be run in parallel, where as many USSPs as possible can be involved, as long as they are referring to a common airspace representation. The question is, can we deal with a group of flight plans at a time, instead of checking it one by one, as with the Fcfs approach? In this case, as you can imagine, there would be some space to perform optimization, where the efficiency of deconfliction could be improved, and also the priority issue might be managed in a more flexible way. And this is actually the key question that we would like to address in this study. And more precisely, we have proposed an optimization model that can be used in both these operational scenarios. One is called this batch optimization, namely each USSP is still going to work individually to look up the flight plans subscribing to their service. And the other one is more centralized. Flight plans from various USSPs are put together. So there should be much more flights in a single optimization instance. And then depending on the availability of flight plans along the time scale, it can be run periodically to synchronize the solutions. Now, one may argue that such a centralized architecture may be not in line with what is expected from the CONOPS, right? Thus, we have considered a way to convert the centralized optimization towards a decentralized coordination scheme. And traditionally, as shown in this diagram, it is assumed that all the input, like the flight plans, are collected from the USSPs as a broker, to the same workspace. And then a central unit, for instance, like say ISP, Common Information Service Provider, will compute the global optimal solution. And this is a traditional centralized architecture. But the model proposed in this study allows us to actually break down the single problem into various subproblems through a dedicated mathematical approach. And it is envisioned that the operators submit the flight plans to the subscribed USSPs, and each USSP locally manages the database of the flight plans within its own workspace. And a central unit is still going to be required, but the main function will be limited to the coordination tasks, exchanging specific information across associated USSPs. And using this scheme, we expect to obtain the same global optima as if in a centralized way. Okay. Some quick brief about the model formulation. In general, the objective function is to minimize the overall delay costs for both linear and aerial flights. And a weighted cost can be specified for an individual flight to reflect its priority level. Say for example here, as presented in Coros, some operational constraints are specified based on their submitted flight plans, which of course are different between linear and aerial flights. Well, the most important constraint is the separation assurance. The idea is that at each valid airspace volume, it can be only occupied by one flight within a valid sliding time window with the length of the separation minima. And the reason I'm saying valid is because there would be some pre-processing to remove those volumes and times that are predicted to not have any conflict issues. And by doing so, we can largely improve the model's computational performance. And say this figure, so we have we have 3 linear flights using the same volume at different at different they are reaching the same airspace volume at different times, as highlighted in red color. And if we're using this format of flight plan similar to the main aviation, then it's quite simple. We just need to move this time window from top to bottom and add every single cell, add up every cell inside, and ensure that there will not be no more than no more than one cell at one time. Yeah. However, once we have considered like those buffer volumes and the special area flight plans, it becomes a little tricky. For instance, in the bottom box here, we captured two cells occupied. One is here, the other is here, but they are actually from the same flight, L3, as you can see. Yeah. So one represents the essential volume, and the other is actually its buffer volume. And this is actually, to cope with the issue, we have devised a piecewise function and converted it into a linear formulation and incorporated in the whole model. Let's see some illustrative examples. The experimental setup is presented here. A 3D airspace of 2.5 square kilometers with 150 meters height is divided into 50 times 50 times 5 identical airspace volumes, and 200 flights coexist during the 24 hours duration. The initial flight plans are randomly generated, including their submission order. And of course, any of these numbers can be adjusted. We simply choose these values for illustrative purpose. We have tested 4 case studies. Case 1 uses purely Fcfs, whereas case 2 uses full optimization, both of which can, of course, showcase some boundaries of the solution. And you can see that around 40% of the total delay can be reduced. And in case 3, we use a hybrid mode. Namely, for the 50% of flight plans submitted at an early stage, we deconflict them as a whole with the optimization approach. Then for the remaining 50%, we continue the deconfliction one by one with the Fcfs approach. And so basically 2 approaches are like appended, with each other. And you see the delay increases. For case 3, the delay increases, then case 2, in particular for the area flights. Yeah. And finally, in case 4, we divide the group of flights into like 6 batches, that is 4 hours per batch, and group the associated flights in each batch based on their submission time. As shown in the table, there are still some slight gains in delay reduction than case 1. If we have if we have more flights included in the illustrative example, normally we should have even better results.
The 15 minutes is up now, so if you are reaching the end of your presentation, that would be beneficial.
Okay, thank you for the notice. I'll finish it in 2 minutes. Some additional experiments have been conducted. For instance, remember the objective function of optimization was to minimize the total delay cost. So that's purely aimed at the efficiency. And what if we use the solution of Fcfs as a reference and include the deviation to Fcfs for each individual flight in the objective function? Yeah, and this could be considered like a way to balance the efficiency and fairness. And we have tested different weighted costs between them, as listed in the table. In addition, some sensitivity analysis have been performed, including the optimization propulsion, batch size, separation minima, and they're conducted in both situations, with or without the fairness concern. Here are the results as expected. The higher the fairness factor is, the more delays required, and of course, closer to the Fcfs solution. For case 3, the hybrid mode, if we have more flights submitted at an early stage, that's being solved with optimization, then the total delay will decrease. For case 3, For case 4, if more flights are involved in each optimization batch, then efficiency will improve a lot. And this shows the potential advantage of using the decentralized coordination scheme that we mentioned previously. And finally, the impact of changing separation minima can be seen in the last figure. And basically, the more challenging this deconfliction problem is, the more benefits it could be achieved by using the optimization than the Fcfs approach. Conclusions and future work. So in this study, basically an optimization model for strategic conflict resolution is proposed with a view to addressing the inefficiency of the existing Fcfs approach. Depending on basically the availability of flight plans and the time when decisions need to be made, the optimization approach can be customized jointly with the Fcfs approach. And we have considered 4 case studies, including F4 Fcfs, F4 optimization, and hybrid plus a batch execution one. And results suggest that compared with Fcfs, notable delay reduction can be achieved with the optimization approach incorporated. Well, some critical questions still remain open, in particular with the priority issue and the fairness concerns. I'll quickly close this presentation. One of the key directions that we are aiming at is to incorporate this RTTA concept, reasonable time to act, which is a very interesting topic proposed in the chorus. Basically the idea is that if an operation plan has been submitted before its RTTA, then the RTA, the service will protect the flight from any further change. And if the operation plan is submitted later than its RTTA, then it will be processed at a disadvantage. Okay, so we are actually working on this RTTA implementation, which we are incorporating both this optimization and Fcfs into an integrated scheme following this RTTA principle.
Thank you very much.
This is all from Osaka. Thank you very much.
Thank you very much, especially for adding this very last slide, which if I understand, is even further than already submitted in your article. So this is very interesting indeed. We have received a question in the Q&A session, and I encourage our listeners and audience to include any further questions here if you have. Jorge has asked, how do you think should you deal with the airspace equity issues? And also I saw in your presentation that you mentioned fairness as a question. Do you have any idea on that already?
The fairness issue you were talking about, right?
Yes.
Yeah, I mean, in this particular study, we have tried to touch upon these issues, but not in a very detailed, systematic way. Because I mean, this topic is it's very important, I would say. And from our study, what we have done is just try to use the Fcfs solution as a reference, and we put like a trade-off between efficiency and fairness, both in our objective function of the optimization model, because we assume that Fcfs is the kind of fairness criteria that can gain the consensus from different operators. So we put them together in the objective function and use different weighted factor to look at the trade-off between them, the efficiency and fairness. But yes, I mean, in our future work, this is one of the issues that needs to be looked into. And I would say this RTTA concept is actually, I think, one of the ways to provide more flexibility in addressing this issue. But since we haven't finalized the work, I would not comment on the final solution, and we will update it in the future work.
Okay.
Thank you.
Thank you very much, and thank you very much once again for the very nice presentation. And I wish good continuation for your work, because this is indeed very interesting and promising for the future. Thank you.
Okay, thank you. Thank you very much.
Thank you. I would like to ask the organizers, have we been able to establish a voice connection to our next presenter? Because it was a question.
We have not been able to contact, but I've seen he was able to connect to audio. So I think he might be able to talk.
Okay, César, can you hear us? And can you talk to us, of course?
He's not unmuting.
Je hebt de kans niet gekregen om te kijken, zeg ik, voor de studie. Sorry? Zeg, je hebt de kans niet gekregen om te kijken voor de studio.
Hello, can you hear me?
Hello, yes, loud and clear.
Yeah, sorry, I had some issues, admin issues, and you also had to unmute me.
Okay, hi, welcome, and very glad to hear that you can finally make it, César Nieto. It's my pleasure to introduce you. You have to know about César that he is a system engineer at Airbus, UTM. He holds an engineering degree in aeronautics from the University Polytechnic de Madrid. And he has worked on aircraft design as a stress and loads engineer before joining Airbus UTM, where he develops simulation tools and collaborates on urban air mobility projects. So César, the floor is yours. I hope that you can share your screen. And at the same time, while listening, I strongly encourage the audience once again to submit the questions in the Q&A stream, because that's how we can ask at the end.
Okay. So I hope you all can see my screen now.
Yes, works perfect.
Okay. So first of all, I would like to remark that I am only the presenter of this work, because this has been the output of our group composed by Vincent Mouillet and Angela Nuik at Eurocontrol Innovation Hub, and also Jorge Chornique and Miguel Ángel Vilaplana and myself, César Nieto, here at Airbus UTM. So let's start. As a starting point, I would like to give a little context information. Our aircraft performance model is part of DeLorean project. DeLorean is a Horizon 2020 project focused on promoting the use of EGNOS and Galileo as enabler to UAM services. As part of this project, there is an air taxi scenario, including a route optimization model, which requires the use of an aircraft performance model. This performance model has been developed in cooperation between Eurocontrol and Airbus. Eurocontrol added his knowledge in developing aircraft models, and Airbus provided experience in developing UAM eVTOL prototypes. So our objective was to produce an aircraft performance model for an ethical vertical takeoff and landing vehicle suitable to be used for future research and also for UTM automated services. So first step, the vehicle. To produce any kind of model, first of all, we need data from a vehicle. So for us, our obvious choice was to use Vahana. Vahana was a single passenger or cargo or electric fully autonomous eVTOL demonstrator that was developed by Acube in Silicon Valley. You can see here in the screen, close to this concept view, the main characteristics, the maximum takeoff weight, payloads, cruise speed, and so on, and range, maximum range. But I also have intentionally added a photograph of the flying prototype to highlight the fact that we are using data from a real flying vehicle. that for this kind of vehicle, it is not an easy task to find. So let's go to the math. We are going to talk about 4 following ballots: the motion equations, power required for horizontal flight, propulsion, and operations. So motion equations are based on the modeling approach of BADA-H. BADA-H is a performance model developed recently by Control to model helicopter performances. Our objective is to analyze the performance of the vehicle from an air traffic management point of view. So we need to simplify the problem. For us, there is no need to calculate the angle of attack, the side slip, the control surface angles of deflection, or other variables that are more related with the handling qualities of the vehicle. So instead of solving the 6 degrees of freedom equation of the rigid body, we use the equation of energy that we are showing in the screen. This equation correlates the power delivered by the propulsion system, called here P, the acceleration, the derivative of the speed with regards to the time, and the rate of climb or descent, the derivative of the height, the altitude, with regard to the time, with the power required to perform horizontal flight at constant speed. Here in the equation, P sub rec. Another additional simplification is related with the fact that the electrical vehicle do not changes its mass with regards to the time, because we are not burning fuel at all. So except that we are at some point of the flight, we are leaving some payload, or some passengers are going in or out, that can be seen as an initial condition problem. The mass of the vehicle remains constant. Instead of that, it is necessary to calculate the consumption rate of electric energy for any flight point. In our operation, B is the energy stored in the battery, and E is this energy consumption rate. So what is the objective of our aircraft performance model? The objective is to obtain a mathematical formula that, or means that allows us to calculate the power required for horizontal flight and the energy consumption rate for any flight point. If we obtain these mathematical relationships, with the help of the energy equation, we can integrate the trajectory of the vehicle and obtain the evolution of the energy consumption along the flight. So this is very easy to tell. It's not so easy to achieve, because rotorcraft have more complex aerodynamics than fixed-wing airplanes, and also multi-rotor aircraft are more complex than single rotor. And if you put the multiple rotors in tilt wings, this is also more complex. And Bahana has 8 rotors on tilt wings. So, and we cannot introduce a CFD calculation in our simulation, because this will be very compute costing. So we need a more simple approach. What we have done, it is to use the already existing BADA helicopter model formulas and mathematically tune them to reproduce the main aspect of Bahana aerodynamics. Currently, the BADA helicopter model calculates the power required for horizontal flight as the product of a characteristic power by a dimensional coefficient that is calculated by this huge formula here with plenty of coefficients that depends on the traction coefficient and the advance ratio of the rotor. And these 5 C sub P R coefficients that are the ones that characterize the specific aircraft, because these formulas are generic for any helicopter, and only the values of these coefficients are used to characterize each single aircraft. But this was not enough for us because we were not able to reproduce the power required. So we have introduced another extra degree of freedom. It is to allow the model to use variable rotor speed. For helicopters, it is considered that rotor angular speed is constant. But for our model, we have introduced a dependency of this rotor angular speed with the flight speed as a fifth degree polynomial of the speed. Here you can see in the chart with solid lines, we have the original Bahana data, and with that line, the output of the model. So there are some irregularities of the original data that cannot be reproduced in the certain zone, some bumps. We are satisfied with the overall behavior of the model. Propulsion is another key point. Electric engines are actually simpler to model than jet or piston because they have constant efficiency and there is no big impact of altitude or temperature on power output. Nevertheless, batteries are much more complex to model than fuel. Power output depends on the state of charge of the battery, the ratio between the actual energy stored in the battery and the total amount of power it can store, and the temperature. And also this capacity depends on the state of health of the battery and the historic of charge-discharge cycles, as the hysteresis has also impact in the capacity. But as all this casuistic is very complex to modelize, we have to settle for ourselves very clear objectives. We need to calculate power losses due to heat dissipation in the battery, and we need to calculate the limitations that the battery has in producing instant power for the vehicle. So for power loss calculation, we took a very simple approach. The battery is modeled as a variable voltage generator connected to a resistor. And the output voltage of the battery and this internal resistance are modeled as a function of the state of charge of the battery and the current delivered to the system. These formulas and the ones used for the power requires are generic. Our intention is to apply them for a lot of type of vehicles, but the coefficients shown here, these B0 to B4, the R0 to A4, and I0 to RI2, are the ones used to particularize them for each vehicle. For the moment, no influence of the temperature is introduced, as it was assumed that the refrigeration system of the vehicle will keep battery temperature control and in the desired working range. So using the equations of this electrical circuit and this modelization of this variable, we can derive the function that provides us with the power losses as a function of the power required to the battery. So once we know how much power we need to drain from the battery and provide to the system, we can obtain these losses that are only in producing the battery. Apart from this, battery introduces another two limitations. First one is the maximum amount of current that the battery can deliver instantly. That for sure has a limit. And the other one is the minimum voltage the system needs to correctly work. These requirements can be written in mathematical language as shown here. And it is also found that the state of charge of the battery has governs which one of these two restrictions apply. For the upper part of the state of charge, the limitation in current is the one that applies, and for the lower part of the state of charge, the one that is imposing the limitation is the voltage, being the transition in a middle point that depends on the battery type. This is really a key feature because this shows that the performance of the vehicle is not only limited by the performance of the motor, the rotor, or the control surfaces, but also by the amount of power that the battery can deliver. This could be also critical for the final phase of the flight, when the batteries are reaching the lower part of the state of charge range, and probably some maneuvers cannot be reachable by the vehicle. And here, once the physical part of the model is produced, it is necessary to deal with operations. And surprisingly for us, this has been the more difficult point to deal with, because today there is no large eVTOL currently operating. To cope with this issue, we have used what was available. That, for example, was the Uber Elevate's mission profile document that was published some months ago. And the gaps we have found in the literature, we have tried to fill using some guesses. For example, it seems logical that the operator impose some limitations on the level of acceleration that the passenger is going to suffer, because I'm sure that a 2.5 G turn, it is not an agreeable experience, and the operator will avoid passengers in this experience. So with all this proposed operations model, we can calculate a full trajectory from vertical takeoff to vertical landing.
And this is your 15th minute, but I see that you are actually reaching just the end of your presentation.
Yes, just 2 slides and I will. Okay, yes, for non-limitation of future work. Once we have the model has been produced, there are two main questions. Is the model general enough? And what is to be done in the future to improve it? And from our point of view, the weakest point of the model is clearly the lack of information available. Even though we are using real vehicle data, it is necessary to prove a formulation against other vehicles. This will allow us to refine the formulation or confirm our assumption, but this is clearly a pending work to be done in the future. And of course, as previously stated, the operations will really need more work. Probably future research work in this topic will help to fill this gap. And just to conclude, for conclusions, 3 points. First of all, Eurocontrol and AirViewCTM, we have developed a new UAM vehicle model based on data from real flying eVTOL. And we think that even with all its weakness, it is a model standing on experimental data that is a very, very important point. Also, model is based on a currently IPM implementation that is BADA and BADA for helicopter, that has shown to be precise enough for traffic management application, and it's already used in multiple applications. And just to finalize, even though the physical model needs to be validated with our vehicles, we think it's a good starting point for future development. That's all from my side.
Thank you very much, César, for your presentation. And as I was listening to your presentation, and I was listening to the challenges you have had there were some which I made particular notes of, like the batteries, the peculiar aerodynamics, and the operations, which seems to be the biggest ones. Which one do you personally or your team personally consider as the biggest challenge among all? So as you were conducting the study, which one made you sweat the most, or which one did you find the most difficult to work around?
From a point of view, I think there are 2 points. One is the most difficult from the technical point of view, that is the aerodynamics, because this really a very complex issue, and probably this is very dependent on the external shape of the vehicle and the configuration of the rotorcraft. Also, full rotorcraft vehicles will differ from tilted wing ones. But I has already mentioned, I think the critical point, one of the most critical point here are the operations, because we have no idea on how these vehicles are going to be operated and also integrated in an urban environment.
Indeed. And this would have been my second question. So which area do you expect still to change, or which could have a biggest influence on what you have achieved so far? But I guess then this is also the answer to this question, or would it be something different?
No, I think really we have two points to improve or confirm, that are the aerodynamics and the operations.
Indeed. Okay, thank you very much for this extremely interesting presentation. It's very good to see. So this is very close to the TRL level, which can already be included into a further level of operations, even though we don't have the history of the operations yet, and no concept for that, or no real matured concept for that. But still, it's very interesting to see that there is already some very sound and concrete stuff that can be used for implementation. Thank you very much for your presentation, César.
You're welcome.
Okay, and then this leads us to the last presenter of this session, who is Nabil Hagag, who is Chief Strategy Officer now with Vestlux. He also has his own bureau, actually, engineering bureau. As a company owner, he has had his bureau since 2020. And before that, he completed Master of Science Mechanical Engineering at the TU, so the Technical University of Darmstadt, and mastered in Fraport, with Fraport together. And this is how he reached his experience and university degrees. And now he is going to be our third presenter, if he's here. Hagag, can you hear us?
Yeah, sure, I can hear you.
Okay. Would you be prepared to start your presentation now?
Sure.
Sure, great. Okay, you have 15 minutes and we are eager to hear your part.
Perfect, thank you. I want to also welcome you from my side. My name is Nabil Hagag, and today I present you the study about our paper about the maximum total range of eVTOL under consideration of realistic operational scenarios by me and my colleagues from the Technical University of Darmstadt and the Frankfurt Airport. Let me maybe introduce you to the agenda. It contains at first the introduction, after that also the state of art, the methodics and the results, and in the end I will come up with the conclusion and the next steps. So let's start with the current situation. The aviation industry has experienced a significant growth through the past decades, although the industry is significantly hit by the COVID pandemic, but it's foreseen that the growth will come up soon. Because of increasing of the urbanization in cities, a countermeasure for gridlocks in megacities needed, and ever more people live in megacities and need to get from A to B in a safe, fast, and ideally economically way. Usually, airport capacity get increased in order to satisfy this growing demand, but the areas are limited, and in order to stay competitive, airport operators are continuously looking for new business opportunities. And a strategic first step towards electrification of air traffic is therefore a promising technology with various business models to benefit intermodality. And this sustainable way of traveling by electric-driven aircrafts like eVTOLs, electric vertical takeoff and landing vehicles, or commonly referred also as air taxis, was born. So amongst others, there are one essential aspect from an airport operator's perspective, which contribute to the success of the air taxi technology, are the promised key data like operating range and performance realistic and achievable today and in the middle term. The problem is there's no realistic evaluation for the range of eVTOLs. And the aim of this study is to prove the technical feasibility of eVTOL under operational aspect and compare the eVTOL concepts and give a validity check. So on global objective, the paper summarized the evaluation, energy demand and consumption, also the realistic ranges based on operational and external factors like emergency procedures and weather influences. So if I come up to the state of the art, there are currently over 500 eVTOL concepts with a large variety of technologies and architectures. Essentially, the architectures can be classified using the categories wingless, like multicopters and quadcopters, also lift and cruise model, tilt rotor, and vector and thrust model. The battery acts as a core element in the electrification of eVTOL. It does not only determine the performance and consistently the possible range, but also the lifetime and significantly influences also the weight and cost of an eVTOL. And therefore, lithium-ion battery plays a key role as a common battery technology in automotive, but also in the eVTOLs. So the problem, as I mentioned, is there's no common calculations for eVTOLs, especially for the power and energy requirements and also for the realistic ranges. But we can derive the knowledge from flight dynamics of helicopters like momentum theory, energy theorem, thrust of propellers and rotors, drag polar, lift to drag ratio to calculate the power demand during hover and cruising flight, as you've seen here in as equations on this slide. If I come up to the methodic, what we use to calculate the ranges, at first for realization to calculate, we have to derive the energy demand during hover flight, cruising flight, and the provided energy. And I want to mention here that we had two different open propellers and shrouded fans accordingly to Leishman about this contract parameter alpha W. That is really an important parameter. And for our calculations, we come up with this range equation, which you can see over there. And we neglected during our calculations few points. What I want also to highlight here, it's the acceleration and deceleration phases, the downwash effects, startup of propellers and engines, electrical consumers, and explicit the consideration of ascent and descent phases. And we used the eVTOL characteristics, what is published, and also using realistic references for influencing factors like temperature and winds on battery, what is also common in the automotive industry, to calculate in the end in a macro tool the realistic ranges and also the maximum possible hovering time. So we have chosen some selected scenarios and we have done a sensitivity analysis, as you can see here, what was based on the flight altitude of 500 meters above sea level with the connected air density, different hover time from 1 to 10 minutes. And we're using the weather data based on the CDC open data of the DVD, Deutsche Wetterdienst from Frankfurt, especially for the region of Frankfurt, for the key parameters air temperature, like the 5 coldest, the average and 5% warmest windy days, And also we was considering the headwind speed, like no headwind speed, the 5% windiest days, the average, and the maximum wind speed during the region of Frankfurt. And we considering the battery development during the next years. So let me show up the eVTOL performance data. However, few reliable data has been published by the manufacturers of validated in experiments. And we estimated also all the parameters for our study. These parameters there have been also discussed with 6 experts from the departments of flight mechanics and aerodynamics at various universities to confirm also the plausibility. I want to mention that the baseline of the study is hypotheoretical description of similar existing design concept and not an evaluation of available products from specific companies. So if I come up to the results, we divided that up into 4 chapters: the energy demand, hover time, temperature and wind, and battery development. And for the analysis of the technical value, the energy demand for hovering between 0 and 10 minutes for each of the 7 eVTOLs is calculating using the best case scenario, means without any weather influences. The energy demand for a cruising flight between 0 and 60 minutes represent the best case scenario as well. So the following figure shows the normalized energy demand in hover against cruise flight per eVTOL type. As you can see here, it's clear that the vector and thrust model has the highest energy demand during the hovering phase because of the weight and the hover efficiency. If you compare that to the quadcopter, it has the highest energy demand during the cruising flight because of the weight and the bad cruising efficiency. And the lowest energy demand during hover and cruising phase has the eVTOL type lift and cruise model number 2. It results because of the efficient parameters during these phases. This diagram shows the hover time scenario per flight minute per eVTOL type, and the higher the hover time, the lower the range, because of the energy consumption during the hover phase is considerably higher than during the cruising phase. And on average, the range is reduced by just under 10% during a 2-minute total hover time. With a 5-minute hover phase, the range is reduced by up to 30% depending on the eVTOL type. And as you can see here, the vector and thrust model cannot even provide any range due to the high energy consumption, about 5 minutes hover time. And if you consider emergency procedure, like hovering about 10 minutes, the hover phase will be reduced by up to around 75%, depending also on the eVTOL type. In this diagram, the temperature scenarios were evaluated and calculated, and the optimal operating temperature of electric batteries ranges between 10 and 30 degrees. At a temperature of around minus 10 degrees, the battery capacity drops by around 40%. The battery capacity by a high temperature, about 40 degrees, has an average of 20% of its capacity left. As you see here on the right side, the next diagram shows the range for 4 headwinds scenarios, what I was telling before. And depending on the eVTOL type, the range is reduced by 18% at headwind speed of around 5 meters per second. On windy days, like 10 meters per second, the range can be reduced by 22%. And the worst conditions, about 20 meters per second, the range can be reduced by up to 55%. Besides, and this is the question, is if you want to operate during that time. And for the last chapter of the results, the battery development, based on the forecasted battery development, it is assumed that the maximum range of eVTOL will increase over the time as the development in the field of battery technology also continues. Accordingly to the current forecast of research institutes, there will be an increase of the range about 27% till 2025, and the next 10 years the range could be increased up to 48%, and till 2050 it's expected that the range will increase in total about 110%, what was also surprising for us. So let me maybe come up with a conclusion about the study. Based on the calculation of the realistic ranges, it can be concluded that the results of the most optimal conditions matched with the specified range of eVTOL manufacturers. The analysis showed the most influential factors like the hover time, the drag ratio, the battery capacity, especially also the specific energy density, the weight, the ambition temperature, and the influences. And in real operation scenarios, such as low temperatures, like winter conditions, like nowadays, and long hover phases based on assumption of manufacturers, specified ranges cannot be met. But the paper addresses a globally perspective, a base for the regulation for eVTOLs like the SC-VTOL, and also a better and optimized and throughout traffic management system. And on local perspective, airports like Fraport can plan the flight operations and yeah, also estimating business and use cases with eVTOLs, and estimate also beside than this the economics and the investment in that topic. Our next steps lead to 4 major issues of urban air mobility that will need to be addressed in future researches. First of all, that all the calculations we have been only theoretical. So we have to do some more test flights to evaluate also the details. Besides than this, we can consider also hybrid eVTOLs and hydrogen solutions as well. And we have to focus also on regulations like the safety, energy, and especially also autonomous flight. Besides than this, we have to think about the economically perspective, like the affordability of eVTOLs. And the highest important issue is also the society to gain trust and acceptance due to the topic. Yeah, thank you so much for your attention. And if you have questions, just let me know.
Thank you very much for your very concise presentation, just below 15 minutes. Thank you very much for keeping the time so well. And also thank you very much for this very colorful introduction to this concept and your research and investigations. My question would concern about the battery development. You mentioned it several times, and I still encourage the audience to drop in a few questions if you feel like it. But until then, I will ask my question about the battery development. You mentioned that you actually consulted 6 experts from various universities when back-checking your results. Right. So how, and the question is this the same true for the battery development part, or how did you ensure, you say it was even surprising to you how much development is to be expected in the coming years. So what was your main source for this?
The main force was with this specific energy density. The specific energy density, we was calculating that for lithium-ion batteries, as I mentioned, and it's also published in a lot of studies. For example, the Fraunhofer Institute did have done a roadmap, especially for battery development. And nowadays, it's possible that we have an effective energy density, effective one about 250 watt-hour each kilogram, and it's forecasted that we have till 2050 around 600 watt-hour each kilogram. And beside on or based on these, let's say, published parameters, we was calculating also the ranges. I want maybe also to highlight, it's always speaking also about different battery technologies, like the solid battery or the sulfur battery. One key point I want also to mention around here about the batteries, later on it will not be able to gain more energy from the battery. You will have a limitation over there. So that's why we coming up with the solution that we have to consider also hybrid and hydrogen solution, what is really promising in the next future.
Mm-hmm. Okay, and what I was also wondering about, you mentioned that, so basically your investigation followed the original way of doing investigations. You had some hypothesis, and then you counter-checked it against what you can see out there in the industry and in research. And my question would concern, did you see anything, or did you find anything surprising, or was there any how a small detail that you expected to evolve in a different way and you were surprised to see it go into a different direction from what you expected in this area?
So as I mentioned in the end, we was expecting that all the ranges, what is published more or less, you know, contains really technical feasibility, and also not only possible for the best case scenarios. And if we was calculating the ranges during winter conditions, for example, as I showed, the ranges are dropped down, and that was from the operational perspective really surprising to see. For every different eVTOL types, how much the range can drop down, and to evaluate also the use cases for these drones.
So, and this was the most surprising element in your research then?
Correctly.
Okay, thank you very much for your presentation. And for the very vivid discussion and the topics that you brought in with eVTOL. I myself was surprised to hear that actually there are more than 500 concepts out there. I thought and I knew that there were some, but this is really a very high number. And I'm sure that this will consolidate at the end of the day and later, but we'll see. Thank you very much. Yep.
You don't have to forget that there are 500 concepts. The most of them, or 90%, they are only, let's say, concepts like a draft.
Sure. Yes.
So not really valid outside data about them. And around, maybe, let's say, I would estimating around 10% or less than 10%, they are already in the flight test mode.
Oh, I see. Okay. And you considered everything, even when it's just an idea on
correctly
black and white paper. Okay. Well, indeed, still it's interesting to see that probably this is well, not probably, for sure, this is a very exciting topic to look into, and this is why we have so many concepts around.
Correctly.
Okay. Thank you. I thank you very much. It was really a pleasurable session, and I thank all three of you, all three presenters. And the audience. We are now closing this session. As far as I know, there will be no poster teasers at the end. Please confirm. From? Yes, thank you. And so it's
I do confirm, Rita.
Thank you, thank you. And just by showing me the poster, it's I took it already as confirmed that it's the Young Scientist Award, which will Okay, just trying to finish my sentence.
I think the connection was lost.
Yeah, actually, it's very good that it was lost just at the very end. So just the finishing sentence was that we are expecting you for the Young Scientist Award at 15:45. Thank you very much for having participated, and all the best.